So we're finishing up 1.9, 1.10. Lots of review here. I think there's only like one new thing. And then tomorrow we will begin 1.11, which is actually like a review of 2 weeks worth of stuff. I don't even think there's anything new in there. Friday is your work day. Friday's the day that is going to be a homework check. And Friday is the day at midnight that your quizzes due. So if you want to work on the quiz in class on Friday with your classmates or on your own, remember you're allowed to work together. You're allowed to use your notes, all that stuff. Okay? So what we're going to do in these first 4 problems is, review. We're going to do the wholes, vertical asymptotes, and zeros. So it's kind of putting all of it together, okay? First step is to see if it's factored. If it's already factored, great. This part's optional. You know, I like to say what x can't be, and that's anything that would make my denominator 0. I always write it. It just kind of helps me keep my thoughts I have to remember that those are the numbers that can't be 0, that make my denominator 0, so these are bad numbers, and I have to assign them both a job. Remember, the jobs are either a whole or an asymptote. They have to have one of those jobs, and they can only have one job. 50-50 chance. It's one or the other. How do we know which job they're going to have? Well, we will simplify this rational function. Simplifying means cancel any like factors in the numerator and the denominator. So if you cancel, you're a whole. If you're left in the denominator, you are a VA. So we gave both of them a job, right? Cancel, you're a whole. Left in the denominator, you're a VA. Understand that the simplified version of this rational function would be what's left over. And I'm going to do it real quick, if we wanted the coordinates or the ordered pair of the whole, because remember, the whole is actually an open point on your graph, right? It's not just a line like a vertical asymptote. It's a point. So it should have a y coordinate. So anytime you need to find the y coordinate, as a reminder, and we talked about it yesterday, you just plug your x value into the simplified version and simplify it. So that would be -4 minus 2 over -4 plus 3, and we get -6 over -1, which of course is just 6. So if we were graphing that, there would be a whole, an open circle at left 4, up 6. Okay? And then if there is anything left in the numerator, it's a 0, also known as an x-intercept. And there is. X minus 2 is left in the numerator, so we would have an x-intercept at 2, right? If you had to write it as an ordered pair, it's 2, 0. Okay? All right, let's look at the next one. Again, it's factored for me. Take a quick look at that denominator, whether you just file it away in your brain or you write it out. Those are the 2 numbers that cause problems for our denominator, right? Then we simplify. So this is where we have those multiples, the multiplicities going on with our factors. So we just have to remember that really fun picture I showed you yesterday. I'll show you again. So let's look at x plus 1. That is going to cancel. There's 1 on the bottom and 2 on top. So when I cancel 1, how many do I have left on top? 1, right. So I can just change that to a 1. The x minus 3's, 1 will cancel in the numerator, and that will leave me with 1 in the denominator, right? If you have 1 on top and 2 on the bottom, 1 cancels for 1, and you still have 1 left, okay? So, remember we talked about if you cancel, you're a whole, and if you're left in the denominator, you're a VA. So, we canceled x plus 1, but wait a second. In the last problem, if you were left in the numerator, you were a 0. So we have a -1 that canceled, so is it a whole? But we have a -1 that's left in the numerator, so is it a 0? Which one is it? You can only have one job. You can't be an open circle and a point. Open circle means you're not part of the graph. So remember this picture. Who always wins is the vertical asymptote. Vertical asymptote always beats a whole. Whole always beats the x-intercept. So if you have to choose between whole or x-intercept, it's a whole, okay? For the vertical asymptote, we canceled and we have 1 left, right? Because we did cancel 1. There were 2 there. We canceled 1 of them, so is it a whole? And then there's 1 left, so is it a VA? Well, again, VA always wins, Okay? So if you cancel and it's left, left is what is the more powerful. Okay? So do we have a 0? Is this guy a 0? No. It's left in the numerator, but it's that number, that x equals -1, already has a job. Okay? Because remember, if you are in the denominator, -1 and 3 came from the denominator, you have to be one of these two. Okay? Because it's a way to show that it doesn't exist on the graph. All right? Do me a favor and change this to a plus sign. So when we get to one that's not factored for us, you want to first see if there's anything you can do to factor it. And in this problem, I can factor out an x. Oh, that would be an x squared right there. Okay, so I know that x can't be 0 because of this x. And then remember, we talked about this yesterday, so I wanted to give you another one like this. What number would make this 0? Under my finger, if I could just make that a -5, -5 plus 5 would be 0, right? What can I plug in for x and square it to get a -5? Nothing. It doesn't exist, right? This x is that rare situation where there's no problem. X can be anything. If you square it, you're still going to get a positive answer. Added to 5 is never going to equal 0. So 0 is our only problem, okay? So these x's cancel. That makes x equals 0 a whole. What is our VA? Nothing. We don't have one. Remember, you don't have to. You don't have to have a whole. You don't have to have a VA. You could have more of one and then the other, whatever. And then how about 0? Do we have a 0? None. So be careful. It's common to think that 2 would be the 0. All of these come from a factor, like x plus something or just an x. The x canceled. So you can't set 2 equal to 0 and solve it. It doesn't make sense. If it had been a 2x, like if the x had not canceled, you could have solved it, of course, and said x equals 0. Okay? But that wasn't the case. So it's often, there are many, many, many situations where you don't have a x-intercept with rational functions. That's okay, right? Last one, more factoring. Hopefully we're getting better at these. Difference of two squares on top, x plus 3, x minus 3. Difference of two squares on top. This is a chart problem. Two numbers that multiply to get 9, add to get -6. Well, I know 9 is 3 and 3. We can make 6 out of that. Oh, they're both going to be negative, okay? So if you need to make the chart, all that stuff, go ahead. But we have to be able to factor. Okay, x cannot be plus or minus 3, right? Those are the, I'm sorry. X can't be positive 3. Sorry about that. Let me write it better. X can't be just 3, right? 3, not plus or minus. X can't be 3. Okay, how do we tell? We just do a cancel situation. Okay, so we canceled an x equals 3, but 1 is left. Is that a whole or a VA? VA. VA always beats the whole. We have none for a whole. Do we have a 0? If you're left in the numerator and you weren't assigned a job already, you're a 0. Okay? So that's kind of tying together the last few days. Moving on to the next page if I don't got any questions. Okay. What we're doing, we're going to do A and B here. What we're doing with these two is we're going to do the same thing we just did. We're just going to do VA and whole, okay? So we're going to talk about what's happening in the denominator. And then I'm going to teach you one-sided limits for a whole. Yesterday I taught you one-sided limits for a VA, which I'll review in a minute. And this will be our last limit statement that we have to learn. Let me not get too ahead of myself. Okay, so denominator is already factored. Plus or minus 1 is what x can't be. And simplifying, I would cancel my x minus 1s. Right? So I would have a whole at which one? Is it at 1 or -1, guys? Positive 1, right? Whatever would make that factor 0. So when I put a 1 in there, 1 is And I'm pointing that out because I just see mistakes on the pluses and the minuses. Sometimes we just get confused when they're both there, so I just want you to be careful. And so then a VA at whatever is left. Okay, now I took the liberty of graphing this on my graphing calculator, and then I drew it for you. You don't need to graph it. I just want you to see it, okay? So, yes. Why would the whole what? Why? Because this was +1 and this was a -1, wasn't it? If you cancel, you're a whole. So what is that x value right there, Zoe? If I put what x value, if I put an x value right here, what would make that 0? 1 or -1? 1. 1 minus 1 is 0. That's why the whole is at 1. Okay, did I write something wrong? I'm sorry, I'm missing what you're saying. Well, because my denominator, this is what my denominator was. So, it is, right here. That's my VA. X equals... Okay, so I wrote x isn't plus or minus 1. That's where I got those two. When I set each of these equal to 0 and solve, I get 1 and -1. So a shortcut of that is just plus or minus 1. You could write 1 and -1, but it's both of those numbers, right? So if you cancel, you're a whole. So the one that canceled was this one. What is the number that makes that 0? 1. What's the number that makes this one 0? -1. Okay. Okay? All right. So guys, look. I graphed this right here. So you can see that whole is right there. What we're going to do is write a limit statement, 2 of them, for a whole. Okay? So I'm going to come back to this picture. Let's start by writing the limit statements. So LIM of whatever the name of it is, as x approaches. That is never going to change, okay? No matter what. We're used to just putting negative infinity and infinity here. That's for n behaviors, and I'll review that in a minute. Yesterday, we put numbers here. That was the x value of our VA. I'll review that in a minute. Now, I'm going to put the x value of my whole. The x value of my whole is 1. And we're going to approach it from the left. We're also going to write the same exact limit statement, except we're going to approach the 1 from the right. So now, yesterday, tie that in from what we learned yesterday. When you see that superscript, or like looks like it, where the exponent goes, is when you see a minus or a plus there, that's from the left, from the right. Okay, so what does that mean? Well, let me use this graph to kind of show you that. So here is x equals 1, right here. Okay, so that point right there, and you don't need to graph this. That point is 1, 1. Okay, so if I say, let's approach this from the left. Well, the furthest branch of this graph that's to the left is this one. But I'm not even going to use this graph because I can't get to this hole. I can't approach 1 from this branch because an asymptote stops me. So then I jump on to the next branch. And this is me traveling from the left towards 1. I'm approaching x equals 1. What is the y value I'm approaching? 1. Yes, that's what I'm approaching. Guess what? It's going to be the same thing from the right. I'm approaching this open circle from the right, traveling along the graph. I'm getting as close as I can to x equals 1. I'm approaching it. What is the y value I'm also approaching? 1. So when you see, what I want you guys to pick up on, because there's three different limit statements that we're going to talk about. What I want you to see on this one is it's an ordered pair, an x and a y. It's a point. Which one is ever a point? Not end behavior. An asymptote is a line. A whole is a point. Okay? And so I'll cover all three momentarily. Let's do one more of these. Okay? So, Zoe, let me make sure you're good. So I would say x can't be -4 and -2, right? Those are the two numbers x can't be. Already factored, yay. simplify. If you cancel, you're a whole. So I would have a whole at x equals -4, right? And I would have a vertical asymptote at anything that's left in the denominator, which is -2. It didn't ask, and I'm not going to worry about it, but I would have a 0 at x equals 3. Okay? That's it. Now, I actually need this ordered pair. Okay? I didn't do it on this one because I had graphed it for you, but the whole would have been 1, 1. If I plugged this 1 back in there, you would have seen that I got 1. So I need this. To do a limit statement, I need the whole ordered pair, right? Because the y value is what completes my limit. So again, I'm just going to plug -4 into these two x's, the simplified version of the function. Yup, we get 7/2 or 3.5. I don't care. You can use either one of those. It doesn't matter. Okay? And I don't need a graph. I don't need a graph to actually write my limit statement. If you just remember, it's just like an ordered pair there. So let's write the limit statement. The limit of g of x as x approaches, guys, that's never going to change. It's always x, that symbol, but what comes after it, you now are seeing can change. We're writing a limit statement for the whole. So the x value of our whole is -4. From the left, and from the right. What's going to come after the equal sign? What is it? 7/2 or 3.5. Either one would be fine. Okay? So it's just, picture this graph like I just showed you. You're approaching -4. What is the y value as you get close to -4? It's 7/2. It's an actual point. It's not a whole bunch of numbers like -infinity or something like that. Okay? But I will review all three asymptotes with you on the last example. Before we get there, we're going to review two of them real quick here. Of the whole, yeah. And when in our last example, you'll see all three of them together for one problem, so you'll be able to really see the differences. I mean, I promise it's not hard. You'll get it with my way of explaining it with snakes. Okay? Okay. So we're going to write an equation of a rational function with this information. Okay, this looks like a foreign language. Like, think about 3 weeks ago. If I said, you guys should all be able to write a rational function, which is some crazy fraction with polynomials on top and bottom, just using this information. It's kind of intimidating, but don't think of it as intimidating. Look how easy this is. And you kind of had number 9 in your homework was similar to this. So I'm going to call it f of x because they gave me some information there that makes me think the name of this function is f of x. Rational functions are a fraction, so there's my fraction bar. Now, guys, the word undefined is used in math. I'm sure you've heard it before, but anytime you have a 0 in your denominator, which is bad, right, that's when we say undefined. Okay? So that's just another way of saying that 2 is a number that would make a 0 in my denominator. 2 is one of my bad numbers. X can't be 2. And so I know that I'm going to have a factor in my denominator that is x. What am I going to put here? Plus or minus? -2. Because remember, before it was a 0, it was a factor. Remember I told you it's going to be really important to be able to go from a 0 to a factor? Same, that's why. Okay? All right. Now, is this going to be a whole or a VA? Okay? Because that's going to determine if I put a common factor in the top or bottom or whatever. Okay, so I'll come back to that. So use your limit statement knowledge. Zoe, you just said to me, always will it be an ordered pair for a whole? And I said yes. So what I think you should see, I'm hoping you see, is that we have an x value of 2 and a y value of 3. That tells me that that is my whole. It's a little sign. So what that means is x minus 2 is going to be canceling with its numerator. Now, answers will vary. There's an endless number of ways you could write this. I'm going with the most simple. Okay? Like, could I have 2 on top and 2 on the bottom? Sure, you could do tons of combinations. But just think about it. I would cancel those, and I would have a whole. Okay? That's it. Good. Now, what's this other one telling me? I'm approaching an x value, and then I'm going to negative, and my y's are they're going to get to some number on a graph of -4, And when it gets there, it's either going to go up or down. That's the sign of a VA. What that means is, look, let's pretend that that's -4. Think of a snake. You guys live in Florida. You've seen them, okay? As a snake, like it's going towards your garage, right, or your house, right? It's going towards your house or a fence. What does it do when it gets there? Does it go through it? No. What does it do? It goes up, right? It goes up, typically. I mean, I guess it could turn around and go back, but stay with me on that idea. VA limit statements are like a snake. Here I'm coming towards this number, and when I get there, I'm either turning up or down. Think of that snake. That vertical asymptote won't let me keep going. It says, oh, you're either going to go up or you're going to go down. Both of them can go up, by the way. Both snakes can go down. You can have one going up, one going down, the other way, the other way. So when you see this, we're approaching -4 from the left, approaching -4 from the right. It'll always be the same number. And we're going towards negative infinity and or positive infinity. That is the sign that that's a vertical asymptote. So vertical asymptotes are left in the denominator. So this would be +4. Are there other ways you can write it? Sure, go ahead. That's the easiest way to write it. Okay? That makes sense? Let's just look at another one real quick. F of x, fraction. -1 is undefined. That means x can't be -1. That means, for sure, I'm going to have x plus 1 in my denominator, right? Now let's look at our limit statements. 1, as we approach -1, we are reaching 2. What is that? What's that called? What's this limit statement? Is this end behavior? Is it VA? Is it whole? It's a whole, right? Because it's an ordered pair. So I know that at -1, I have a whole, which means in my function, we would have to cancel. And there's the snake. We're approaching +3 from the left, +3 from the right, and both of them, look, my snakes both hit that number and have to turn, because you're not allowed to cross that vertical asymptote. So as they get close, they go up. So that is telling you that there is a VA at x equals 3. Factored form is x minus 3. Good? You guys are doing great. We have one more example, and then I will shut my mouth. Okay? What time is it? Oh, it's getting close. They could be here any minute. And I don't even know why I'm acting like this. I normally don't. I'm a little rebellious at times about stuff like this. I think it's because it's not my administration. I don't know whatever about them. But like other principals. Anyway. Okay. Last example. This is like example 1 and, this is like homework problem 1 and 2. So you definitely want to do this with me and make sure you understand. We're putting it all together, all right? So we're given f of x in equation form. We're given f of x in graph form. I'm going to try and go a little fast so I'm not teaching us so much when they come in. They really want to see. I don't think they want to see me teaching. They want to see you guys working. So I won't speed through it. You guys are more important than that, but I'm just kind of moving. All right, looking ahead, simplified form, coordinates of holes, domain and range, haven't done that in a while, asymptotes, and then all of our limit statements, okay? So, factored for us, great. X can't be 2 and 3. Same thing we've been doing. I think we're really getting this, right? We will have a whole at x equals 3, a VA at x equals 2. It's graph for us. So, simplified form would be whatever's left after you canceled. Good? Coordinates of the whole. Okay, I know the x coordinate, right? I need the y coordinate. Where am I going to plug that x in? Right here, right? Nope, that's a 1. Sorry. Wait. Oh, that's a 2. Sorry. That's a 2. That's a 1. That's a 1. Sorry about that. Okay. Now, could you have pulled that right off the graph? Yes. But in your homework, you don't have the graph. Okay. So know how to do it algebraically, plugging in. Yes, if you have the graph, I would not have spent any time on that. I would have just, if I could read the graph well enough, I would do that. Okay, let's skip domain and range for a minute. We already did vertical asymptote. We stated it up there, right? HA is where a lot of you asked questions yesterday. Don't forget what we learned last week, okay? HAs come from the degree of your numerator and the degree of your denominator. When we learned about HAs, we weren't canceling stuff. Remember that when you do your HAs, it's before you canceled, okay? So that could be tricky, right? So 3x times x is 3x squared. Remember, you need the leading term, and this is in factored form, so I'm just multiplying the leading terms of both of them. So remember, so I'm just putting a note here why I'm doing this, to find my HA. So remember, when 2 equals 2, that's when you look at the leading coefficients, right? 3 over 1 would be 3. Okay? Again, could you have just grabbed that from the graph? Sure, it's right here. Y equals 3. And of course, we have an x equals 2 we just found. Okay? But I'm just telling you, you don't always have the graph, so you have to know how to find it without that. Now let's do the domain, which I messed up last year. I was so mad at myself. Okay, domain is all your x values, starting all the way to the left. Remember, we know that that's an arrow there, so that's negative infinity. And we keep going, and we keep going until something stops us. A vertical asymptote stops us. We have to jump over it, right, to get to this branch. And remember, we always use parentheses on an asymptote because it's not included in the graph. Okay, then we get back to this part of the graph. So everything to the right of 2, but not including it. Anybody know what I'm going to put right here? This is where I messed up last period, so it's okay if you don't know. Remember, this point is not part of our graph. 3 is not included. There's numbers in between 2 and 3, my darlings. They're teeny tiny numbers, but between 2 and 3, you have space. Think of it like that. But neither of these are part of the graph, so that's parentheses. And then we get back on at 3, but not including it, to infinity. Kind of confusing, right? You're skipping over. I think of those unions as where I'm skipping over stuff. I skip over vertical asymptotes in my domain, and I skip over the x value of a hole in my domain. In the range, it's going to be the same thing. I'm going to jump over the y value of my hole and horizontal asymptotes. So we start at the bottom, negative infinity, all the way up to negative 4, right? The y value, not including it. We're jumping over it. Keep going until what? What's the next number I'm going to put here? 3, because that's my horizontal asymptote, right? Not included. Jump over it. And now we're at 3 to infinity. Okay? Almost done. Okay. When you see negative infinity and positive infinity as x is approaching, guys, remember, that's your end behavior. What's happening all the way over there and all the way over there? Those are your ends, right? And in rational functions, we sometimes call them the horizontal, the HAs, right? Well, it's always going to be the HAs. So remember, as I'm going to the left, I can't keep going down, right? I'm going down, going down. Oh, no, my horizontal asymptote of 3 is blocking me. On both sides. It's always going to be the same number. Recognize it. All the way to the left, all the way to the right. In a rational function, that end behavior is always going to be your asymptote. That horizontal blocks you from going up or down, okay? This next one, 2 from the left, 2 from the right. What is 2's significance? X equals 2. What is x equals 2's job in my graph? It's my VA, right? That's the snake, if that helps you. So as I come towards my vertical asymptote, my snake can't keep going to the right. It has to go up. And coming from the right, so on this branch, as I approach 2, my snake can't keep going, so it goes down to negative infinity. Here they come. Last one. Last one. What is x equals 3's significance in this graph? What is it, Kaden? The whole. That's x's significance in this graph. It's the whole. So as we now notice, this is not a one-sided limit. The one I showed you before was a limit coming from the left and a limit coming from the right. In this case, when you don't see a left or a right, you are going to assume it's from both directions. And that can happen on a whole. Let's look at it. Here's our whole at 3, -4. If I'm traveling from the left, that would be this piece, okay, from the left and from the right. As I get closer and closer to 3, x is approaching 3. What is my y value that I'm approaching? -4, okay? So in this case, we were doing our limit statements using the graph. Sometimes you're given the limit statements to create the graph or the function, and we'll work on both of those going forward. Okay, so I'm going to give you your homework assignment, and we will start working. We're on page 105, A22. Now, as you're writing down the assignment, guys, please listen to what I'm going to tell you. I have told you many, many times that graphing rational functions is not necessarily a skill that you have to be able to do. You're not going to have to graph a rational function as part of the AP exam or any of my assessments. It would be a multiple choice where you would have 4 of them, say, and you have to decide between what's given, what your graph is. My advice for sketching these, now these are sketches, which means they don't have to be perfect. Mine look pretty good, but they don't have to be perfect, okay? My advice is use information you have to sketch it. Use your graphing calculator to sketch it. Use your table of values in your graphing calculator to help you with some of this stuff. And I'm going to walk around and help. You guys can work together. But this should not be stressful, okay? We're not going to stress too much about this. This is super, super important, okay? We need to be able to know all these important key features of the rational function, okay? So this will be on Canvas later along with the video. And go. Work together, ask for help. Watch that video. I think it'll be oh. One thing I want to tell you guys, when you do if you use the graphing calculator to graph these, your entire numerator has to be in parentheses, and your entire denominator has to be in parentheses. So if it's in factored form, it's a lot of parentheses. It's a lot of parentheses, okay? So keep that in mind so you don't waste a lot of time, but you have to separate the numerator and denominator. holy shit, look at the asymptote one up on it. Look at it really closely. So, we shift in the graph, asymptote, and you know how you use the parent function? Some other. So I could say it really slowly to the straight up there. Holy shift, look at the asymptote one up on it. So, look at me go, mother function. That's fun. Thanks for being wonderful. I don't think I have to drive you. Right. Your x-intercept comes from the numerator, right? How did you find your y-intercept if you didn't graph it? Plug in 0 for x. You put a 0 right here. 0, 0, put negative 4. Okay? I guess I never really talked about that. mean, not that I know of. Yeah, the end of the